In this video, we'll be talking about some units that we use to measure radioactivity and radiocarbon dating. One way to think about the radioactivity of a compound is how many reactions that are going to happen, so how many decay reactions are going to happen over a given amount of time. The most common unit that we use for this is going to be the Becquerel, so this is going to be the number of disintegration reactions per second. So we can look at an example of this. We have polonium-208. We talked about this before, that it has a first order alpha decay with a half-life of 2.90 years. So what would the reactivity of this be in units of Becquerel if we had a 20 gram sample of polonium-208? And let's see how we'd get to this answer. So what we're looking for is the number of individual decay reactions per second. So first we have to get just the rate of this reaction. We know that it is a first order decay with 2.90 years as the half-life. In a previous problem, we saw that this gives us a K equal to 0.239 years to the minus 1. Okay, so the rate of this is going to be equal to K times the initial concentration. And we have our K, 0.239. And for our initial amounts, since this is going to be in moles, we want to convert the mass. So that's 20 grams. And the molar mass for polonium-208, since it's given there in the mass number, we can use the 208 grams per mole. And that gets us about 0.02298. This is kind of an approximate mass, but this is close enough for this problem. And the units for this, again, would be moles per year, since our rate constant was in years to the minus 1. So that's moles per year. We need individual decays per second, so we have to do a few conversions on this. So this would be 0.0229. And then we want to convert the moles to individual reactions. And then we want to be able to convert those years to seconds. So we have a few conversion factors for that. And if we plug all of those in, we get 4.39 times 10 to the 14th decays per second, or becquerels. These are often used in terms of radiocarbon dating. So one example, when we're talking about carbon dating, we can think about some important isotopes of carbon. So carbon-12 is the most abundant isotope. This is stable, and most carbon is going to be carbon-12. Carbon-13 is also stable. It is not very abundant, about 1%. Carbon-14 is also naturally present. It undergoes beta decay, and it has a very small abundance, but this will be present. So in living things, this carbon is going to be continuously replenished. So while you're alive, you'll go eat some food, you'll incorporate that carbon through biochemistry, etc. So you constantly, as something is alive, you're going to maintain this ratio of carbon-12, 13, and 14. So they'll all be present at relatively constant levels. When you die, you stop eating, and the amount of carbon you get is not replenished. This includes the carbon-14, which is radioactive, and now will start decaying while it's part of the organic material. And so basically this will start a stopwatch where we can lower the relative carbon-14 abundance in the once living organism. This will lower the radioactivity as we have less and less carbon-14. And so what we can do is we can compare the reactivity in a fossil that contained carbon from a once living organism to the radioactivity that is expected, and use kinetics to determine how long it's been decaying or how long ago it died. So for example, say we had a 30 gram sample of carbon that was discovered in an archaeological dig, and it was determined to have a radioactivity of 3.9 times 10 to the 5th becquerels. The initial decay rate of carbon-14, this is 5.5 times 10 to the 4th becquerels per gram. You'll see this a lot in some of these units of radioactivity that they're given per mass, so you have to do a little bit of calculation to get your expected value. The half-life of carbon-14 is 5,370 years. And so we'll use this to try and figure out how old this sample is. So the first thing we need to do is figure out the expected amount for a 30-gram sample. So we'll take this 5.5 times 10 to the fourth and multiply it by 30 grams. And this gives us that an expected amount would be 1.65 times 10 to the sixth becquerels. So you can see this is higher than what we found in our archaeological sample. We can now look at the equation that we'd use for first order kinetics to compare these. So we have A is equal to A naught times e to the negative kt. We have our initial amount and our final amount. We want to find the time, and to get k, we're going to have to use this half-life. So k is going to be equal to the natural log of 2 divided by t1/2 for our first order reaction. This is going to be equal to 1.29 times 10 to the negative fourth, and that's in years to the minus 1. And so now we can solve this equation and start plugging some things in. So if we solve this for t, this gives us the natural log of a divided by a naught. All of that divided by negative k is equal to t. And as we plug in the values, this is going to be the natural log of 3.9 times 10 to the fifth divided by 1.65 times 10 to the sixth, and all of this divided by negative 1.29 times 10 to the negative fourth. If you plug all this in, you get a value that is 1.118 times 10 to the fourth, and for our time, this is in years. So based on the radioactivity of our archaeological sample, we'd say this thing is about 11,000 years old.